Hi, Assalamualaikum. My name is Muhammad Adi Ahrami bin Talmizi. We are from Group 10. We'll present Laboratory Report, Proportional Control, Liquid Level and Flow System. So here our group member is Muhammad Harid Sufian bin Muhammad Zulkifli, Muhammad Alimi bin Muhammad Adam, and the last one is Muhammad Asmil bin Yunus. So we will go to the first presenter. Hi, Assalamualaikum. My name is Muhammad Adi Ahrami bin Talmizi. So I will start the presentation with additional theory. So for the additional theory, proportional control is a crucial control strategy in liquid level and flow system. It adjusts control output proportional to the deviation between set point and process variable. The gain constant determine the strain of the control action, while the arrow signal derive the action. Proportional control is essential in advanced control strategies like proportional integral derivative (PID) control. Understanding proportional control helps engineers and research tune parameters, analyze behavior, and makes informed decisions to optimize performance. Next, I will continue the presentation with the objective. Objective of this experiment is to describe how to proportional control algorithm works. Second is to define offset. Third is to describe the system using lab list transformation. And the last one is to observe the action when running the system using proportional controller. Next, I will also continue the presentation with the equipment and apparatus. So equipment and apparatus for this experiment is the first one, process line panel for level control. Next is PC computer with processor motion software. So I will pass to the next presenter. Thank you.
Hello guys, my name is Muhammad Sofian bin Muhammad Zulkifli and my matrix ID is DD220090. So now I will continue our presentation about procedures. For the task 1, inventory and safety checks. The materials required for this activity, make sure need to check whether it's available or not at the lab station. And then the inventory and safety checklist on worksheet need to complete for this activity before start this task. For the task 2, setting up. For setting up, we need to turn on the computer, and then we need to run the process motion software. The pressure line at the panel active, making sure that the panel is connected to a COM port on your computer, and that the communication key is turned to PC. Drain the tank so that it is at a minimum level, and then close valve A and keep valve B open. Valve C should remain closed throughout. Next, online was clicked in the process motion software add modes. The level control and process button click. Select the PNID controller from the dialog box and enter the following parameters, like set point is 120, KC is 5, TI is 100,000, TD0, MO0. In setting the parameter, you have to create a system where the TI and TD and MO parameters will not contribute to the final M. M will be equal to KC. E, this is a strict proportional control algorithm with no BS. Run click to see the response of the system to reach the steady state system, and run the system until it reaches the steady state after 80 seconds, and analysis the graph show to see the offset. And the system output H in column I measured to the chart on worksheet, and column is marked until reference value. The value in every row of the column record the controller output M in column 5 of the chart on your worksheet. For task 3, using the proportional control. First, the level control button need to click and change the KC setting to 10. Now the performance to set the input, increase the set point by changing into the initial reference value 30%. Record the new set point value in column 2 of your chart and click run. Wait until the system reaches steady state. Record the error in column 4 of the graph on your worksheet, and record the controller output M in column 5 of your graph, which need to wait for 80 seconds. The total response time reached at the steady state minus time recorded in column 6. Record the percentage of the offset error in column 7. For 6, lastly, reset the set point back to initial reference value and allow the system return to the reference value. Lastly, we talk about task 4, vary the KC value. The KC value change to see the change of the system, vary the KC setting to see how the proportional control affect the system response. First, the initial reference value in task 1 to 3 of set point will reset. Then click run and allow the system to come to the ready state. Change the KC to a value of 100. Perform a setup input by increasing the set point by 30%. Now present the system with alert by opening valve A and closing valve B. Valve A drain more quickly than valve B, thus putting an added load on the system and click run. Both valve A and valve B will open. Analyze the response of the system and measure the data in the result. Change the KC to a value of 1. Perform a setup input by increasing the set point by 30%. Click run to describe the general system response and the response time and the percentage of offset. Change the KC to a value of 10. Perform a setup input by increasing the set point by 30% and click run. Lastly, save all the graph from the data from task 1 to task 4 in the Microsoft Word and move the data to student email to make a lab report for final finding. That's all from me for the procedure. Thank you.
Thanks to the presenter before me. Before I continue with this presentation, let me introduce myself first. My name is Muhammad Al-Ilmi bin Muhammad Adam and my metric number is DD220086. Here we can see the result for the task 2. The purpose of doing task 2 is to set up the net experiment. The value we get in the task 2 will be used in the net experiment. Here we can see the result for the task 3 in the table. The reason for this task 3 are using to proportional control. Value for the KC we need to set up to 10. In the task we need to find the percentage of offset in the highest and the lowest. We also need to find the cause for the offset happening. Finally, for the task 4, we need to find the value for the KC. And here we can see the value that been recorded throughout during the experiment. This is for observation. The proportional control method is used in this experiment to show how the control system works. To distinguish between a dynamic and static system, it evaluates the time constant, the error of the system response on the gain of the controller. Material must be accessible and in the good operating order to provide a correct result. The panel is safely attached to the COM port, and the water level is maintained to a minimum. Every 80 seconds, the system must wait for the state to stabilize before accessing the data. The sensor recognizes the system which use prevent input to maintain the tank water level. If the water level fall, the pump turn on and fill the tank.
Hello guys, so now I will continue again with the calculation.
Here we show how the calculation need to be done to complete the table of the result. The second column in the table need to be calculated. The formula that need to be used is IRV multiplied by the percentage of the stage, and the multiply value need to be added to the IRV value. The value for the 0% is the same, which is 120. The value for the 30 percentage is 137.8. And here we can see the final value and we have obtained after calculation process is done.
We go with the calculation for column 7, which is over RV, which is column 4 over column 2. And plus it with the percentage. And we can see the percentage for 30%, 40%, 50%, negative 20%, negative 30%, negative 40%. You can see the value Start with 11.67%, -1.5%, 4.72%, 1.25%, -7.08%, 8%, and 1.57%. So that's all from me in calculation.
So I will continue the presentation with graph analysis. So this is a result for task 2. So for the graph analysis for the task 3, as we can see, this is a graph for 30% and 40%. So at this part, we can see the graph for 50% and negative 20%. So here is the graph for negative 30% and negative 40%. So this is a graph for task 4, which is KC 100% valve A open and valve B closed. And next is KC 100, which is both valve is open. And this is a graph for KC 100 valve A open and B closed. And the next one is KC1, which is both valve is open. So the last one for task 4, which is this is a graph for KC10, which is valve A open and valve B closed, and the next one is KC10, both valve is open. So I think I will pass to the next presenter. Thank you.
I continue again with the discussion. So for discussion, we will discuss about the question on the procedure from the task 2, task 3, and task 4. I will continue for discussion. The question on the procedure for task 2. The question is there an offset? No, this is because the system at set point 120 and KC5 is in the steady state conditions and no intercept between blue line and green line in the graph for task to show. Task 3. Question describe the system output response. The system output is 137.8 have offset have shown that there is have offset because the value of error is -2. And the question 2, what is the cause of offset? The difficulty in determining the system's steady state due to its inability to correctly establish the steady state condition is the root cause of this offset. Due to the level sensor's incapacity to measure itself, there will be an inaccuracy because the difference between the output of the system as a whole and the reference output will be stability difference.
The first question for the task 4 is describe the general system response. The response time and the percentage of offset. KC is 100 and the reference value is 138 with valve A open meanwhile valve B closed. The system takes 30 seconds to reach the steady state condition and the error is -1 and the error percentage is -2.17%. The second question is how does the system respond? The system takes 71 seconds to reach the steady state condition and the error is 3 and the error of percentage is 2.22%. In addition, the condition of valve when valve A open and valve B closed take less time which is 67 to reach the steady state compared with when both valve A and valve B were open which is 71 seconds. This is because the valve is open. Water will flow out through the valve and the pump will keep running as water is pumped into tank to maintain the same water level as the input level. The third question is describe the general system response, the response time and the percentage of offset. In this task, the value of KC is set to 1, while the both valve A and valve B were open. The system shown that there is no response time to reach the steady state even though the value of error is very big which is 74. In addition, the system can achieve the steady state because the value of KC is very small to get the system read. So the pump can work functionally and cause the output value is difficult to control by the pump. The fourth question is describe the general system response, the response time and the percentage of offset. When the KC change to 10, the value of error measure is 7. This is because the system shows that steady state is achieved and the value of error reference value is 5.07%. The question 5 is how does the KC affect the system response time, the offset, based on the KC is 100, KC1 and KC10. A faster response time is typically the result of KC having a greater value because it amplifies the control action. The system arrives at the desired value faster. A high KC can also lead to higher percentage of offset or overshoot, though as the control action might become overly forceful. A smaller value of KC, on the other hand, lengthen and the response time while shortening the offset.
So I will continue the presentation with a conclusion.
In conclusion, proportional control is a promising control strategy for liquid level and flow system, but understanding system dynamic and tuning the proportional gain are critical factors for optimal performance. Future experiment and research could explore the integration of proportional control with other control techniques to enhance system efficiency and robustness.
So I think that's all from our group. Thank you.